Good morning, Black Hat. We would like to welcome you to the second day of the Black Hat briefings, and here we're presenting Stopping Injection Attacks with Computational Theory by Robert J. Hansen and Meredith L. Patterson of the University of Iowa.
Thank you, Black Hat. Thank you, Raven, for the introduction. Today we're going to be talking about, obviously, stopping injection attacks with computational theory. Over the last 6 months, Meredith and I have isolated some theoretical constructs which show great promise in limiting injection attacks. Not just SQL injection attacks, but anything from XSS to command shell injection to a whole panoply of options. We're going to be presenting the theoretical results first, and that's going to involve a little bit of math, and I'm sorry about that. But the math is important because that way you can be absolutely certain that we are not trying to pull one over on you. I see that there are lots of other speeches about SQL injection slated for Black Hat, and I believe that what makes ours different is we have the math on our side. So we hope that you will consider that, and we hope that you will stay awake through the math portion in order to get to the very interesting technical and code portions. So, before we can really talk about theory, we need to first define the problem. Because if we do not have a good understanding of what the problem is, we are not going to get a good solution to the problem. We've all seen this happen before, where a half-witted solution to a problem is usually worse than the original problem itself was. We want to avoid that, so let's talk very specifically about SQL injection. In its broadest strokes, our problem is that users input garbage. GIGO is an acronym common to us all, but it goes a lot further than GIGO. In the modern day, we deal with complex systems in which garbage input doesn't create garbage output. Garbage input leads to compromised systems. This is also very important because think about how many times your web server gets attacked. And then think about how many times completely clueless users completely screw up simple directions and input meaningless information. Anything that an attacker can do to your web forms, a common user can do to your web forms too. And given how many more clueless users there are out there, it's more likely you'll be running into problems from this front first. So, not only do we have a big problem with input validation, we have no good tools to keep garbage out of our systems. Our current input validation techniques, what you will see on these slides as IV, are largely ineffective. We are dealing with an awful lot of false positives, an awful lot of false negatives, and perhaps what is worst, we don't use them at all. We don't know whether people refuse to use them because of laziness or whether because the people writing web applications know just how limited our input validation techniques are. It doesn't really matter. The current techniques are pretty much worthless and need to be improved upon. The current state of the art in input validation says to use regular expressions to validate user input. However, everybody who's done any serious web programming knows that this has a serious false positive and false negative rate. Some legitimate inputs will be incorrectly flagged as bad, leading to user frustration. When this happens enough times, users will turn into paranoid conspiracy theorists and will go to a competitor's site. False negatives are also a huge problem because if you're allowing in malicious information which will crash your system will be down, and then users will go to other sites. For too long, the entire question of validation has been phrased in terms of guns or butter. We can have this or that. We can have convenience or we can have security. It surprises me that it has taken so long for us to realize just how stupid this choice is. If we are choosing to make errors, then we are choosing to make errors. Why are we putting up with such a broken scheme of operation that we say the best we can hope for is to have serious errors? Why does conventional wisdom encourage this one or the other, guns or butter approach? And shouldn't we try to find techniques which will reduce the error rate? And how much more robust can our infrastructure be What kinds of new applications will we be able to develop once we have a robust infrastructure for validating user inputs? This is a quote from Luke Willen and Laura Thompson's PHP and MySQL web development from Sam's Publishing, 2005. In a semi-random survey of books on the shelves at Barnes & Noble, this was one of the better books out there about input validation because it actually talked about input validation. For the benefit of the MP3 recording, I'll recite it here. Be careful when making data validators more restrictive, though, because a validator that rejects 1% of valid input is far more annoying than one that lets through 10% of invalid data. When I read this, it leaped out at me because it is so barkingly bad. We are saying that it is far, far better to allow malicious inputs in that can crash our system than to deny legitimate users the ability to execute odd but valid queries. We have to completely do away with this completely broken mindset. Willen and Thompson weren't unusual. As I said, they were some of the better writers out there. In our survey of about 10 commonly available web development books, only 2 discussed validation in any detail. The other one was an O'Reilly text, which basically said input validation is a really hard problem and we're not going to talk about it. So if something as broken as the last slide could get through the technical review process, that means one of 2 things. Either the technical review process was brain dead, or else our best practices are brain dead. Given the overall high quality of the book, I think the latter is far more likely. We are lying to ourselves when we say that we can only have convenience or security. If we do not have both, we will not have either. Convenience must be secure, otherwise we're condemned to 0-day and script kiddies. Security must be convenient, otherwise nobody will use these systems. False positives and negatives are categorically unacceptable. We must seek more accurate technologies. Our belief that we can have only one or the other is crippling web security. What a lot of web developers fall into the trap of thinking is that it is far, far better to wall off everything, to make very strict regular expressions, far better to reject valid inputs than to possibly accept anything invalid. This is a fortress mentality. From inside your web development, it looks like you're living in a castle. From outside, it doesn't look like a castle. It looks like a coffin, and it has just about as much life in it. We cannot do this. So what we have done is we found a way to apply some theoretical tools from computer science to give us almost perfect protection against injection attacks and almost perfect protection against false alarms. I emphasize here, almost perfect. There is absolutely nothing that we can do to save developers from incorrectly using our tool. But if you correctly use it, you are going to have an extremely robust system. So that's the basic overview of the problem. So let's start talking about the theory of the problem. Anywhere you have user input, you need to validate that input. This should be axiomatic to all of us in the room. Unfortunately, all of us in the room probably work with people for whom this is a breathtaking revelation. I suggest that when you get back to your businesses, when you get back to your consulting firms, you bring a LART with you and spread the gospel. Injection attacks are a specific kind of input validation problem. You want to allow users to change the flavor of a command string, but not its functionality. That might not make much sense, so I'm going to expand upon it in just a little bit. You may be asking why nobody has tried to solve this problem before. And the reason is because a man named Beiser, who is very, very smart, a genius in the field, in 1983 showed that the problem of input validation is intractable. That's math weenie speak for you really don't want to try it. The input validation problem is AI complete. Once you have a program that can completely validate all inputs, you have a program that can tell you about the meaning of the collected works of Benedict Spinoza. Basically, it is very, very tough. But we have found islands in this problem space which are solvable, which are applicable to all kinds of injection attacks, and which we think are really cool. So some of you may not be familiar with what injection is, so let's go through a little bit of an example. Let's take select rights from access table where password equals foo, where foo is just standard Perl variable interpolation. It works great if foo is just something sensible for a password. It fails utterly when you start embedding quotation marks into it. Now we have the SQL statement, select rights from access table where password equals blank or 1 equal 1. This is, not to put too fine a point on it, not a good thing. So the first question then, the most important question, is how can we differentiate injection attacks from legitimate inputs? For that, we have to go into computational theory. This part may be a little bit dry, and I apologize for that. However, like I said, we want to make it very clear that we are not pulling one over on you. In order to talk about input validation, we need to talk about syntax and semantics. These are two words which are not all that often talked about in the business IT world. Syntax is the structure and order of a sentence, and semantics is its meaning. The best example that I can give of this comes from Bill Clinton, where everybody agrees on what precisely he said. We all agree on the syntax. However, there's a lot of argument over what the meaning of the word is. That's all semantics. So a legitimate input to a SQL statement will only change the semantics. It will not change the syntax. Now, in Meredith's portion of the speech, she's going to give a little bit of an explanation for why I'm hand-waving a little bit here, but take my word for it, it's basically propeller head stuff past that point. An injection attack will change syntax and semantics. If we take a look here, we have added or 1 equals 1. Those are additional syntactic elements. We don't need to understand what it means. We just need to be able to see that the additional syntax exists. Computational theory is a branch of mathematics which is concerned, very intensely so, with syntax and semantics. Computational theory works by encoding math problems as strings, and then we use devices like regular expressions to compute on those strings. As soon as we're done with our computation, we have some way to translate that string back into the answer, and congratulations, we're done. If this sounds very, very boring, you're right. There's a reason why I slept through it in graduate school. Now, computational theory is what we use to discover the absolute limits of computers. If computational theory says you can't do it, you can't do it. That's not even worth trying. So let's look at regular expressions from a computational theory perspective. The first question we have is, can regular expressions handle the kind of complex syntax which we are likely to see in SQL? And if they can't, why are we trying to do input validation with them? Computational theorists don't talk all that much about regular expressions. We talk about something called a finite state automata instead. A finite state automata is the most basic model of computation you'll ever practically use. You take a string of letters, and based on each letter, you move to a new state within the automata. If at the end of the input you're in an accepting state, we say that the FSA has matched. And if it doesn't, if it's not in an accepting state at the end of the input, we say that it hasn't matched. You should already be able to see the parallels between regular expressions and FSA. In fact, you can prove the two of them are equivalent. An FSA has no memory, no recursion, no anything. This means that you cannot do a backref inside a finite state automata. This should not be enough to make us think that these results are not applicable to regular expressions, though, because while many people in the audience today are certainly competent enough to use backrefs, a lot of the people we work with aren't. Let's take a very simple language, a language in which the only two letters are A and B. Or if you want to think in binary, you can think of it in terms of 1 and 0. Either way, it doesn't matter. We want a regular expression which will accept any sequence of AB. It'll accept the empty string, AB, 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 and so forth and so forth. This is what a finite state automata looks like in mathematical theory. We start in state A, and then for each letter in our input, we move to a new state. So if we just wanted to see whether the empty string matched, we start in state A, we see that we immediately end, and we're done. We're in an accepting state. We say, yes, it matches. If we are matching the string A by itself, we go into state B. We're done. But only A and C are accepting states, not state B. So we say this doesn't match. And you can continue on through this finite state automata for any length of string. You can hand it any arbitrary length of string, and this mechanism will reliably match the AB repeated. The only important thing there that you absolutely must remember is this only has 4 states. Every finite state automata has a finite number of states, hence the name. That means that we are going to recycle a state at some point for a long enough string. Okay, so all regular expressions can be described by finite state automata. Finite state automata have a limited number of states, and for a large enough input, you're going to revisit a state. Those are the salient things you need to keep in mind as we go on here. Let's imagine, for sake of argument, that we have a finite state automata which can recognize any number of A's followed by the same number of B's. Can this exist? Will it be reliable? As it turns out, it can't exist. It isn't reliable. It will have false positives and false negatives, just like our current generation of SQL validation techniques. That's why this result right here is important. The pumping lemma is something from computational theory which everybody in computational theory absolutely hates. So I'm going to give you just the absolute minimum here, but later on we're going to give you references to this if you want to see more of it. If we have a long enough input, at some point we are going to have to recycle state. If we only have 4 states, then as soon as we have 5 symbols, we have to revisit a state at least once. This is the downfall of the finite state automata. If after k repetitions of the letter A, we're in a state where we can recognize k repetitions of B, what happens if we go through a few more A's? Can we ever get back to this original state where after having k plus some number of A's, we can recognize k B's? The pumping lemma tells us that we can. Therefore, we cannot have a finite state automata which will reliably recognize this language. We found a language which looks like a regex, but we can't do it. Therefore, we need to have some better, stronger technology. That technology is the context-free grammar, which is the next most complicated, next most powerful computational mechanism. Turing machines come right after this. I'm not going to go there, so relax. The math is almost done. A CFG is a regex which is allowed to recurse upon itself, like a backref. Perl regular expressions really aren't regular expressions. They are context-free grammars. However, to make a Perl regular expression act like a proper context-free grammar, you basically have to write something that looks like a few pages of executable line noise. Now, how this is different from regular Perl programs, I have no idea. But a context-free grammar can generate a string of letters according to a certain set of rules. As it turns out, we can come up with a rule that will recognize this any number of A's followed by any number of B's. Remember that it did not matter before how complicated our finite state automata got. We could have a finite state automata with billions of states, and it still could not reliably recognize this simple language. But with one rule, what we call rule R, we can. Our rule R says we can generate either A, followed by another application of rule R, followed by B, or we can generate nothing. Those are the only 2 things we can do. And with something this simple, we can recognize that language. This is the power of self-reference. So, you can see right here a couple of derivations of how we get empty validates. We go from rule R straight to nothing. AB validates because we apply R, we get A followed by R followed by B. R goes to nothing, leaving us with AB. And so forth and so forth and so forth. We recurse down through this context-free grammar, applying rules as we go. And here is the same thing done visually. This is the string AABB. This is how we derive it, using that one simple rule. Now, there's a question which some of you may be having as to, wait a minute, with finite state automata, he was talking about recognizing strings, and now he's talking about generating strings. Why the change? What's going on here? And the answer is that from a math standpoint, they're the exact same thing. It doesn't matter. If you can generate a certain string within the rules of a context-free grammar, we say the context-free grammar has matched that string. That's all, nothing more. So we have now found something stronger than a regular expression. We have found something that is capable of recognizing this more complex language. If we needed user inputs that matched any number of A's followed by any number of B's, we literally couldn't do it with a regular expression. It wouldn't matter how hard we tried or how complicated it got. We would always have false positives and false negatives, just like we have with SQL injection. We needed a context-free grammar instead. And this leads us quite directly to our first major axiom of input validation. If you're going to validate your inputs, you have to do it with a mechanism strong enough to validate the input. Regular expressions aren't that strong. Therefore, stop using regular expressions to validate inputs. SQL is a context-free language. If you're going to validate inputs to SQL, you need to use a context-free grammar. There are many other context-free languages which are in common use today. HTTP, HTML, XML, SGML, command shells, programming languages. This is a huge problem space that we have stumbled into. And this basic technique of using the right tool for the job applies to a huge number of things which right now we have no effective tools for. Okay, so let's talk a little bit more about what we've covered so far. HTML and SQL are both called context-free languages, and they both need context-free grammars in order to validate them. We have seen regular expressions, we have explored them a little bit mathematically, and we've seen some languages that they cannot validate, specifically context-free languages. We have seen the hacker word of mouth tells people to, 1, not validate at all, and 2, if you're going to validate, use regular expressions. But we know that doesn't work now. So the only conclusion we can draw is that all of us are living in sin. And this leads us to a couple of recommendations from theoretical computer science about how to validate inputs safely and effectively with high reliability and accuracy. The first one is never validate a naked user input. You need to validate the user input as it is going to be used in whatever context it's going to wind up. If a user is allowed to input a string which is going to be plugged into a database query, you need to validate that entire query, not just the user's input. You also need to use the right tool for the job. You need to understand the complexity of your problem and use a tool appropriate to that complexity. And the most subtle point here is don't get stronger than you have to. User input is almost by definition outside your defenses. It is your first line of defense. It is going to get hammered on 24 hours a day, 7 days a week. It is going to get hammered on by clueless users, by script kiddies, by hardcore black hats. It is a good bet that at some point your input validation mechanism will be compromised. This could be because of a bug in the library that you're using. This could be because the web application programmer didn't understand the tool like he thought he should. It doesn't matter. What matters is expect it to be compromised. So we have a question here. If we're going to be exposing something, knowing it's going to be compromised, do we want to give them a strong mechanism, like the Turing machine, which can do anything that any computer can do? Or do you want to give them the weakest tool that they can use? You want to use the weakest tool that will do the job in order to limit the damage that somebody can do by compromising that tool. I said earlier that if you are interested in the mathematical portions of this talk, that we would be revisiting that subject. There are two excellent books on computational theory which are plenty worth reading. One of them is Art Fleck's Formal Models of Computation. The other is Michael Sipser's Introduction to the Theory of Computation. Professor Fleck is at the University of Iowa, so we're biased. But Professor Sipser is over at MIT, so if you trust MIT more than the University of Iowa, feel free to read him. If you want to know more about input validation and the formal computer science behind it, please read our paper, Guns and Butter, Towards Formal Axioms of Input Validation. Now, we submitted the PDF to Black Hat, but apparently they decided it wasn't interesting enough to put in that big phone book you're carrying around. So you're going to have to take a look for it on the web instead, and that's pretty much illegible. So I will just read that address off, which I should be doing anyway for the benefit of the MP3 record. http://cs.uiowa.edu/tilde/P2005.pdf. It's on the CD? Excellent. Thank you. And our final recommendations are stop thinking about validation in terms of convenience or security. If you think about that in terms of convenience or security, you're going to make trade-offs which you mustn't make. The entire idea of one or the other is killing both. We must have both, or we will have neither. And at this point, I'd like to hand off to Meredith so that she can start talking about how we put computational theory into practice with a library which we have decided to call Dejector.
All right. So, first of all, now that we've got all this useful math, the next question is, how can we use it in the name of truth and justice? As a practical note, the grammar definition file for PostgreSQL is about 10,000 lines all by itself. Perl regular expression backgraphs are hard enough to implement already, so nobody's going to want to re-implement the entire grammar just for a single web application. There's also the problem of ambiguity. Most programming languages, and SQL is no exception to this, need a parser that can examine both the current piece of input, which we call a token. You can roughly think of a token as anything that's separated by white space, and the next token, which we call the look-ahead token, in order to figure out exactly which rule to apply at each step in the derivation. Context-free parsers are hard enough to implement on their own, and look-ahead parsers are worse. I've been doing this stuff for about 8 years now, and I've never even tried. So you need some help, basically. The good news is most programming languages rely on what's called a parser generator to, say it with me, automatically generate look-ahead parser code based on an abstract definition of the language. So if anybody's ever heard of Berkeley Yak or GNU Bison, that's what we're talking about. And that's going to be our first step in building an automated tool to perform context-free input validation. So, just as a reminder, our focus here is only on the syntax. Every time we apply one of these context-free derivation rules like Rob was describing, we can record that application as a node in an n-ary tree, and once we've derived the entire string, we have a complete syntactic representation of it. A normal SQL query string and a query string with extra SQL syntax injected in are going to have different syntactic representations. It's a pretty abstract way of putting it, though, so let's take a look at how it works. Consider the following SQL statement. Select rights from access table where password equals black hat munged. There's one specific set of rule applications in one specific order which produces that query. So all we have to do is cut down the set of rule applications to only the rules which produce that query, and we end up with a heavily restricted grammar which will not admit any injection attempts because any changes to the tree result in an invalid tree. Whoops. So that sounds difficult, but the good news is that we can do this by example rather than having to write up a new grammar every time we do it. Or rather, we can acquire the grammar from a known acceptable statement. But we don't even have to go to the trouble of generating a new parser because, like I said, order matters too. Only the strings which result from the same rule applications in the same order are valid, so we can get the same results by comparing two parse trees. All right. So this is a tree for the query which I showed you before. Select rights from access table where password equals, well, in this case, string. Good luck reading that. It looks big and hairy, and it's actually a reduced version of the real PostgreSQL syntax tree for this. A couple of things I want to point out. You may notice that most of the nodes in that tree are in brackets. We refer to those as non-terminal nodes because obviously they're not the leaf nodes. The ones which are leaf nodes, you'll notice select, writes, from, access table, et cetera, et cetera. Those are not only leaf nodes, they're also unbracketed. So each one of those is going to fall into some category. Either it's going to be a keyword or it's going to be some user-submitted piece of input which doesn't actually match any of the syntax keywords. So instead, we lump that into what we call a token. Integer would be a token, string would be a token. I haven't represented that on the syntax tree just because I ran out of room, but it's there in the code. All right, so you'll notice that an acceptable parse tree, such as this one, where the only thing that's changed is the password, has pretty much the exact same shape as the canonical parse tree that we're looking at. The only difference is in the semantic content of the password down in the very right-hand corner. On the other hand, an injection attempt has an awful lot of extra nodes. You'll notice there's this entire expanded right-hand subtree that isn't there in the previous version. The shape is pretty radically different. There's an entire extra level of depth in that Boolean comparison on the bottom right. And this is simple enough for humans to spot, and it's blatantly obvious if you're walking the tree as well. All you have to do is compare the nodes of the tree one for one, and once you get to a point where they differ, you can reject the input. So let's take a look at a possible real-world example. Say that you've just been to the bookstore, you picked up a copy of PHP for Dummies, and you've blown right through it. You've got a big book collection which you've stored information about in a database, and you want to build a web interface so that you can access that information without the pesky command line. So let's say you want to be able to list all books that were published in a certain year. You build a simple web form which has one field. In your PHP script, that field corresponds to the variable $form input. Problem is, even with the help of functions like pgescape string, this approach is still vulnerable because all an attacker has to do is tack on a semicolon, add another command, and there's all your hard work down the drain. Now, you can certainly use other functions like isNumeric to make sure that the variable you expect to be an integer really is an integer, but the more functionality you want to add, the more checking you're going to have to do, and that can be a pain in the ass. It would be nice to be able to accept more free-form input, but using traditional validation mechanisms, there's really no good way to do that safely. The run-of-the-mill way to handle this kind of interface is to create a form with an input field for each column that you're willing to let into your where clause, then validate or escape all those fields individually, and then once that's done, concatenate all of the inputs which actually have values together into one single string. That's an awful lot of code all by itself. Then, on top of that, you need to perform regular expression validation over the entire query to make sure that nothing spurious has been introduced, like extra comments. And that's where you run into the pumping lemma problem that Rob brought up earlier. It's too easy to end up with a situation like a substring of quote, quote, dash, dash, quote, where the first two quotes describe an empty string, the double dash marks the start of a comment that extends to the end of the line, and the final quote is just part of that comment. So using traditional mechanisms, you're screwed. So let's take a step back and see if we can't make this a little more intuitive. One problem which is sometimes hard even for experts to solve is unexpected data. It's easy to think of examples of what you want to see. Predicting the unpredictable is hard. But we already said that if you can specify a good example, then you can validate against that example. We call that an exemplar string. So remember earlier you saw the good test query that had the same tree structure as the exemplar string? They varied only in one position, that terminal node containing the password. So all we have to do is indicate to whatever function compares the two trees, hey, we don't care what terminal lives under this node. So we do this by bracketing the password substring in the exemplar query with curly braces because curly braces don't have any special meaning in SQL, at least not the Postgres dialect. So once we know which substring we want to ignore, we parse the full query, we store the tree as XML, and we look in the parse tree for the lowest node which completely encloses that substring. Then we decorate that node with an attribute indicating that it's mutable. So when a user submits a query, we then parse that into an XML tree as well, and we diff the two XML files, skipping over the subtrees of any node that has the mutable attribute set. This way, any attempt at injection leads to rejection, which leads to dejection. We've done our initial work on PostgreSQL because the grammar definition files are freely available, but we could easily apply the tree comparison code that we've written to any other grammar definition. So how do I use it? Well, our gold standard for usability here is, does this take advantage of what I'm already thinking of, and does it avoid making me think of an infinite number of possible attack cases? We've written an underlying library in C, and we've put together some swig wrappers already, which provide an incredibly simple syntax that takes advantage of that usability approach. So let's take a look at how we do it in Python. Step 1, instantiate a dejector object using the bracketed exemplar query that you already came up with. Then, prior to sending any query that a user submits onto your database, you call the .validate method. If that method raises an exception, then guess what? You've just caught an injection attempt, so handle that in whatever way you best see fit, and you're done. 3 steps, that's all. So the one caveat that I do have to point out here is that it's important to have a properly written exemplar query. In theory, this is 100% accurate, but unless you write your exemplars very carefully, you can still leave yourself vulnerable to injection. By properly written, I mean an exemplar which isn't too permissive and which also doesn't misunderstand the way that tokenization and parsing works. All right, so what do you want to not do? First of all, don't bracket the whole goddamn string. This should be pretty brain dead obvious, but you know, people do stupid stuff. For that matter, don't even bracket large portions of the exemplar if you can get away with it. As a rule of thumb, if you find yourself bracketing phrases of more than 2 or 3 words, you're probably doing something wrong unless you're dealing with a clause that has a lot of keywords in it. On the other hand, in most SQL dialects, clauses that have a lot of keywords in them are usually pretty special case anyway. So a related problem that's a little bit more subtle is the problem of crossing over rule boundaries. In the example that I've got up here, where foo from bar in select foo from bar where username in special user.name, the brackets actually cross over 2 separate nodes beneath simple select, which is what a select query actually parses out as. If you take a look at the BNF definition, Bacchus-Naur formation, the abstract grammar for PostgreSQL, that simple select node is actually going to have a total of 8 children. I simplified it on the tree that you saw earlier to give it just 5. Some of those nodes are going to be empty. So anyway, what happens if you branch over 2 sibling nodes? If you bracket over 2 sibling nodes, what's going to happen is you're going to end up flagging their parent node as mutable. And that means that your entire select clause is going to get flagged as mutable. It's a lot safer to handle mutable items such as column names and, on very rare occasions, table names, things that you're looking for in a table, whatever, as individually mutable. So if instead you just bracket the foo and the bar and whatever else, that's going to be a lot safer. And SQL keywords aren't really going to change anyway. I mentioned tokens earlier, and the keyword select is always going to get tokenized as select. So don't worry about whether to flag keywords or not unless you really desperately want to make an entire large clause mutable. All right. One more thing on tokens. So the input to the parser is actually created by a thing called a lexical analyzer, or a lexer for short. Just like a parser is generated by a parser generator, a lexer is generated by a lexical analyzer generator, in this case GNU Flex. As I'd suggested before, SQL lexical analyzers break on white space. They're gonna break up a string, wherever they see white space. And because we want to keep our lexer and our parser as close to Postgres' advertised behavior as we can in order to avoid introducing some new unintended and exploitable behavior, we really have to stick with that limitation. So you can't bracket just a portion of something that gets recognized as a standalone token. It's wrong to try and bracket just one digit in an integer, because that integer is what's going to get tokenized. The lowest enclosing node is going to be the token name integer, and so you're just going to be recognizing any integer that's there. So it's really in a developer's best interest to get as familiar as they can with the syntax of whatever language they're using anyway, in order to avoid falling victim to any mistaken assumptions. But you already knew that, right? Right? Okay. All right, so finally, just a couple of words on licensing. Rob and I are both very strongly in favor of open source, free software, however, whatever name you want to apply to it this week. We've already released libdejector PG under the GNU General Public License. That said, we are also pursuing a patent because, well, quite frankly, we need the money pretty badly. On the other hand, we also really want to see this get used in the real world. So if you're interested in working on an open source implementation, come talk to us. For that matter, if you're interested in working on a proprietary implementation, come talk to us. Seriously, just talk to us. We like to talk. And here's how you can talk to us. We are Rob Hansen and Meredith Patterson at the Department of Computer Science, University of Iowa, Iowa City, Iowa, 52240. RJ Hansen at cs.uiowa.edu, and ML Patter, MLPATTER, at cs.uiowa.edu. Yeah, Hansen with an E, by the way. You can also grab a copy of the source at svn://acm.uiowa.edu/svn/libdejector, and there's going to be a SourceForge page going up real soon now. So, with that, any questions? Right, so the main difference that I see between parameterized queries and the kind of stuff we're doing is that a parameterized query is necessarily going to be hard. You don't really get a lot of spaces to fill in the blanks. And like I was describing earlier with the book lookup scenario, instead of putting, so a parameterized query would be one way of handling that, right? You would have individual fields for all of the properties that you could look up stuff on. But that really doesn't give you the ability to pass in a more fluid query safely. With what I was describing, it would be possible to to pass in a whole bunch of different arguments to a where clause, and then validate those against an exemplar query safely. And it just gives you a lot more flexibility, basically, is what I'm saying. But it manages to do so in a secure manner.
Not only that, but there's also the matter of the techniques that you are describing are specific to SQL. More accurately, they are specific to whatever your vendor's implementation is. What we are talking about here is computational theory, which applies to a broad variety of different languages, different problem domains.
Right.
SQL is just one small, this is an example, a proof of concept. The larger ideas can be applied many more places than the technology you're talking about can be.
Yeah, you can't really apply parameterized queries to things like HTML injection. Yes.
by taking the statement that you send to your database or otherwise use and apply it to, say, a dummy database or some fashion where you're not exposing your real one, and make a statement that would normally fail.
Right, and that is kind of the poor man's version of what we're talking about, because the first thing that touches the query in that dummy database is going to be the query parser, and we've basically lifted the query parser code wholesale.
Yeah, but the idea was, you're right, you have a very general way of discussing it. It occurred to me that if we could get some more input out of the guts of the parser, go to a database vendor and say, look, can you supply us with some more information about what the hell your parser found when it got this input for rather than arbitrary processor? If you could get some of that internal state, then you might be able to test more easily the
But the internal state is not actually necessary.
sounds like you're describing the internal state. You're getting out the parser back to the database vendor and supplying you with the parser tree.
No, we're not talking about internal state. We're talking about only the syntactic rules.
Well,
When I-
that's
when I hear
a kind
about,
of
when I hear
internal
about,
state. I see what he's saying.
When I
but-
hear about internal state, I think of things like semantic application, things like that. All that we're asking for is the language definition. Once you give us the language definition, we can do the rest ourselves.
Yeah, which is why we've been doing our development against Postgres, because we get that for free. MySQL's the next victim. So,
The thing is, you also want to, there may be some value in using the real parsers because people who write these parsers do different strange things.
yes, we are using the real parser. The only thing that I've ripped out, trust me, I spent like 3 weeks writing this. The only thing that we've taken out of the parser is the semantic actions that are attached to the rule applications. We've swapped out those semantic we've swapped out those semantic actions for semantic actions which instead just generate XML nodes saying, "Hi, I applied this rule." Yes.
Have you done any work or considered like compiling either to targeting an intermediary language so like pluggable with these languages, or
That's actually not possible because the way that these things work is that every single SQL vendor on the planet has their own implementation, their own customizations, their own quirks. If you can find any one SQL vendor that is 110% ANSI SQL conformant,
There's not one. I know somebody who checked.
yeah. So we have to have these customizable modules because otherwise you wouldn't be using the exact same language that your database does, and that could be a problem.
The good news, though, is that the back end to this, the part that actually does the XML comparisons, is completely portable. All we have to do at this point is grab the Bison file, strip out the old semantic actions, put in the new semantic actions, and you're done.
Oh, I think we should also point out that it's portable across Linux, FreeBSD, the BSDs in general, and it will run on Mac OS X as soon as somebody ports the GNOME XML libraries to Mac OS, specifically GDOM.
The query was just also, suppose you're in a shop that insists, for whatever strange reason, we use DB2 or Oracle. How might we go to Oracle or IBM and try twisting their arms and saying, look, can you put out something that would be useful in this process?
If you
IBM
find
is
out,
easy.
let me know.
IBM is easy. You go to them, you say, there's a cool open source project. You guys want to be known for helping open source. Give us the language definition. But for Microsoft, I think that involves a liter of blood in your firstborn child. Yeah.
All right, I think
Okay.
we're out of time, guys.
If you still want to have questions for us, we're going to be here for a little while afterwards. So it's been a pleasure talking to you all, and have fun at Black Hat.